Okay, dear students, today we have discussed the topic asynchronous up counters. As we know, counters are the two types, synchronous counter and the asynchronous counter. In case of the synchronous counters, we apply the clock pulse simultaneously to all the flip-flops. But in case of the asynchronous counter, we apply the original clock pulse on the first flip-flop and then output of the first flip-flop is connected to the second one flip-flop. Okay, so we have discussed the 2-bit asynchronous up counter. Two-bit asynchronous up counter. For developing the 2-bit asynchronous up counter, we require the two flip-flops. We take the T flip-flop. T is the input, output is the Q and the Q complement. Suppose there is a FFA, flip-flop A, and second one is FFB, flip-flop B. FFB. Okay. It also has the input T, subscript TA, QA complement. Here outputs Q, B and QB complements. In the toggling mode, we know in the T flip-flop, for toggling mode, we connect the input to the logic 1. So here we connect both the flip-flop inputs, that is T, to the logic 1. Logic 1. We take the concept of the negative as triggering. Negative as triggering. That's the clock. And in case of the asynchronous counters, we connect the output of the first flip-flop to the clock signals of the second flip-flop. So QA is connected to the clock signals of the FFB, flip-flop B. Okay? So that's the logic circuits for the 2-bit asynchronous up counter. Here we see that we have not applied the clock signals simultaneously on both the flip-flop, but we apply the clock signals only first flip-flop, and then output of the first flip-flop is connected to the clock signals of the flip-flop B, or you say the second flip-flops. Now we start the working operations of this flip-flop. Initially assume both the flip-flops have the contents 0, 0, means QA and QB equals to 0, 0, means both the flip-flops are in the reset states. Both the outputs are on 0, 0. QA equals to 0 and QB equals to 0. That's the initial state. Now, as we know, this is the negative state of flip-flops. Okay, so when we apply the first clock signals after the first after applying the first clock signals. What happened when we apply the first clock signals? Then TA flip-flop FFA or TA will toggle because it's accept the negative as triggered clock pulse and it's toggle means it's change the contents. Initially its output was 0, QA equals to 0. Now it will be 1. So after the first clock pulse, QA equals to 1. QA equals to 1. Then logic 1 signals goes to the clock signals of the second flip-flop or flip-flop B. Since it is the negative edge triggered flip-flop, so it does not accept the logic 1. It's operate on the negative edge triggering. So FFB will not toggle and the contents of QB will be equals to 0. So after the first clock pulse, the contents of both the flip-flop will be Q equals to 1 and QB equals to 0. QA toggles, QB not toggles. And now after that, after applying the second clock signal, what will be the contents? After applying the second clock pulse, the FFA or TA flip-flop will toggle again. So the contents of the QA will be equals to 0. QA equals to 0 because last time QA equals to 1, so it's toggle after applying the second clock pulse, so it becomes again 0. And what happened on the FFB or TB flip-flop B? Since FFA is toggle, flip-flop A is toggle, so 0 is connected, QA output is connected to the clock of the second flip-flop. So 0 comes on the second flip-flop FFB and it's again toggle. It's treated as a negative edge triggering, so it's toggle now. And the contents of the QB becomes equals to 1 because QB last time equals to 0. After toggling, the contents of the QB equals to 1. So we can say after applying the second clock pulse, the contents of the QA equals to 0 and QB equals to 1. Now after applying the third clock pulse, what will be the contents? After applying the third clock pulse, TA again toggles. So contents of the QA equals to 1 and QB equals to 0 because after applying the third clock pulse, TA toggle. So on the second clock pulse, QA equals to 0. Now it becomes after toggling 1 and after the second clock pulse, QB was 1. So it's again not toggles, means Q equals to 1 connected to the next clock pulse. So 1 comes here, it's treated as a positive edge triggering and QB not triggered, so QB equals to 1. So in this case, after the third clock pulse, QA toggles, flip-flop B, FB not toggle. So again, if we apply the next clock signal, third, fourth, after applying the first, second, third and fourth clock pulse, what will be the continuous? Now, after applying the fourth clock pulse, PA, flip-flop, FFA, again toggles, its contents will be equals to the QA becomes equals to 0 and QA is connected to the next clock of the flip-flop. So 0 comes here, it treats as a 0, it treats 0 as a negative clock pulse. So it TB, flip-flop TB again toggles. So again its contents will be equals to the QB equals to 0, QB equals to 0. So we see that after the fourth clock pulse, flip-flops comes on the initial state, that is 0 0. That is 0 0. So we can say on the QB QB was 0 0 initially. QB QA equals to 0 0 initially. QB QA equals to 0 1 after first clock pulse. After first clock signal, and QB QA equals to 1 0 after second clock signal, and QB QA equals to 0 1 1 after third clock signal. And if we apply the fourth clock signals or fourth clock pulse, then again flip-flops comes on the initial state, that is the 0 0. So that is the working operations of the 2-bit asynchronous up counter. We see that is equals to logic 1, that is equals to logic 1, okay, that is equals to logic 0 1 2 3, and after the fourth clock pulse, counters again jump on the initial state, that is the 0. So in case of the 2-bit asynchronous up counters, total number of states we can count, that is 4, means state diagram 0 1 2 3 and again 0. So that's the state diagram of the 2-bit asynchronous up counters. In case of the 2-bit asynchronous counter, total 4 states we can count 0, 1, 2 and 3. Similarly, we can develop the 3-bit asynchronous up counters. In case of the 3-bit asynchronous up counters, we take the total number of flip-flop, that is 3. TA, TB and TC. Third flip-flop is also connected in similar manner, and the output of the TB is connected to the third flip-flop, that is the TC. Clock of the third flip-flop TC. So by the 3-bit asynchronous up counter, by the help of the 3-bit asynchronous up counters, we can count total number of these states, that is 8. That is 8. Means by the 3-bit asynchronous by the 3-bit asynchronous up counters, we can count total number of states, that is 8. Means 2 raised to power 3 equals to 8. Total states will be 8. That is 0 to 7. 0 to 7. Initial state will be 0 and last state will be 7. 7. Logic 1, 2, 3, 4, 5, 6, 7, and after 7 our counter again jump on the initial state, that is 0 in case of the 3-bit asynchronous up counter. So developing the 3-bit asynchronous up counters, we take the 3 T flip-flops, okay? TA, TB and TC. We can also develop the counters by the help of the JK flip-flops. For developing the up counters by using the JK flip-flop, we showed the inputs J and K. J and K. Because we know that in case of the JK flip-flops, both the inputs J and K are shorted, then it's act as a T flip-flops or it act as a toggle ball. So we also develop the 2-bit asynchronous up counter by the help of the JKFF, like this. Complement. Both the inputs is sorted here like this, and we make a single link. Okay, this is the FFA, and similarly the second flip flop QB outputs are the QB and QB complements. Both the inputs JB and KB are shorted, and so now here we also use the concept of the negative as trigger. That's the original clock signals. Here we apply the logic 1. So there is the 2-bit asynchronous up counter by the help of the JK flip flop. In this figure, we see that J and K input are shorted on the flip flop A and also in the flip flop B. Here also the input JB and KB are shorted, and then both the inputs of both the flip flop inputs, flip flop FFA inputs and the flip flop FFB inputs are connected to the logic 1. and the clock signal is originally applied to the first flip-flop, that is FFA, and the output of the second flip-flop, output of the first flip-flop is connected to the clock signals of the first flip-flop. So that's the circuit diagram of the 2-bit asynchronous up counter by the help of the JK flip-flops. So by this again we can count total number of the state, that is 4, 0 to 3. In case of the synchronous counter, suppose we are discussing the we are developing the synchronous counter, then we connect the single clock pulse on the both the flip-flop. That's the 2-bit synchronous up counter. Flip-flop TA, QA, QB, TB, QB, QB complement, QA complement. Okay. Now, again we take the concept of the negative edge triggering here. Both the inputs of the flip-flop is connected to the logic 1, and in case of the synchronous up counters or synchronous counter, 2-bit, that is the 2-bit synchronous up counters, we connect the clock signals simultaneously to all the flip-flops. So that's the concept of the synchronizations. Means a single clock pulse is applied simultaneously to all the flip-flop. But in case of the asynchronous, this was connected, the output clock signals of the second one is connected to the output of the first flip-flops.